Welcome back to the third day of the Tommy Flowers Network conference. For those of you that haven't attended the previous sessions, I'm Mike Williams. I will be your moderator and compere for the day to kind of get us through the session. Without further ado, I'll hand you over to our host, Fraser Burton. Fraser's the Senior Manager of Network Physics and BT's Applied Research Department. He's been hosting these 5 sessions over the week, and he's going to give you a bit more background on the day and then introduce our first keynote. So, Fraser, over to you.
Excellent. Thanks, Mike. And welcome, everyone, again. This is the third day of the 2020 Tommy Flowers Network Conference, which we're calling Let's Get Physical. As Mike said, I'm Fraser Burton, and I lead BT's Network Physics Research team. And this is the 4th year we have been running these conferences, and I'm delighted to say that we have more attendees now than ever before. That is, without doubt, a consequence of moving online. So it is one of the few dividends of the pandemic. What I would say about the pandemic is that it has really underlined the importance of telecommunications in our lives. Just 10 years ago, it would have been almost impossible for most of us to have been working from home, but now it's working pretty much seamlessly. So I think that really does kind of underline for all of us the importance of a good communications network in our lives. The purpose of the Tommy Flowers Network is to bring together the communications and IT industry together with UK and international academia to help develop the skills and the knowledge base of our future research leaders. So that's our present postgraduate researchers. It's worth kind of understanding who Tommy Flowers was. He was a wartime communications engineer. He worked at the GPO, which was a predecessor organization to BT. He was working with electronic valves and for use in telephone exchanges. But come the war, he started collaborating with the likes of Alan Turing and academics at the University of Cambridge in the code-breaking effort. And that work ultimately led to the development of the world's first electronic programmable computer, which is called Colossus. And we have Tommy Flowers as one of our heroes because he's an excellent example of how industry and academia, by working together, can really make a significant impact on society. And that's what we're hoping for from the Tommy Flowers Network. So this week, very much a thrill for me. This week we are showcasing the fundamental role of physics and physicists and the role that they have in shaping our digital future. However, today we're doing something a little different from the other 4 days, and we are really focusing in on the work of postgraduate researchers, physicists and not. And so the focus for today really is on our researchers. We have an opening and a closing keynote speaker today. We'll be kicking off with Dr. Richard Baghetti, who is Director of the Postgraduate Institute at the National Physical Laboratory. And we'll be finishing with Professor Mike Payne, who is Professor of Computational Physics at the University of Cambridge. The central section of today will be 6 lightning talks from postgraduate researchers who will be competing for the coveted Tommy Flowers Network Award, which is a greatly sought-after award. Never before thought of until this event, but I'm sure it will be greatly sought after. And this will be awarded by Carol Fletcher, who is BT's Senior Manager for Network and Research Partnerships. And we have 3 judges who will be listening and attentively to each of these talks. We have Trevor Linney, the OpenReach Research Director, Dr. Philip Stiles, who is the University of Cambridge Senior Lecturer in Corporate Governance, and Dr. Kishore Sengupta, who is the Reader in Operations Management at the Judge Business School. So we're now perfectly on time, which is lovely. And I am delighted to hand over to our opening keynote speaker, Dr. Richard Baghetti of the National Physical Laboratory.
So thank you very much, Fraser, and hello to everybody out there. It's always quite an interesting proposition presenting to my own screen, as I do every day. But I hope that you can hear me well, and I'm really looking forward to telling you something about Mpl and the Postgraduate Institute for Measurement Science. And I remember, several years ago when the Tommy Flowers Institute, as it was called then, was inaugurated, and being there at the beginning of that as well. I'll probably mention a couple of times that the Postgraduate Institute is celebrating 5 years of collaboration and activity as we were inaugurated, in fact, on the 23rd of October in 2015. So we're all growing and developing, and I'm very, very happy to be here to be able to talk to you about some of the things that we've done on our journey over the past 5 years. And clearly the focus will be on postgraduates, but how physics and the applications of physics really can transform our world. So I need to advance the slide. So just a quick introduction to Mpl, what we are. We're a world-leading research facility with the National Measurement Institute, and at the organization we have over 500 scientists and engineers from a wide variety of fields working together to do some significant things, and we like to characterize it as, saving lives, protecting the environment, enabling people to feel safe and secure, as well as supporting international trade and innovation. So those are sort of big overarching words, and I'll try and put a lot of context around those during the talk, not just in terms of what our scientists do, but certainly what our postgraduate students do and how they develop into doing that sort of thing. One of the key things about Mpl as a national laboratory is that our advice is impartial and independent, and I think that's very important in principle to everybody, but it means that consumers, investors, the whole range of people, policymakers, entrepreneurs, and engineers and scientists can always rely on the work that we do, in the foundations of measurement and standards. And I think that's particularly pertinent and probably poignant in this day and age when truth and verification are really critical aspects, not just of our scientific and engineering endeavors, but in our sort of social and political spheres as well. So a little bit about Mpl, who we are and who we are now, and how we operate. So we are the UK National Metrology Institute, one of many around the world. We're a public corporation. We exist as a formal partnership between Mpl, BASE, the Department of Business, Energy and Industrial Strategy, and a formal strategic relationship between the universities of Surrey and Strathclyde. And of the sort of over 500 plus scientists, there are several hundred more staff supporting those activities, working in commercial and business development activities, as well as a couple of hundred, at least 200 visiting researchers per year, and a couple of hundred PhD students that are co-supervised by Mpl scientists and engineers. And we partner with a large range of organizations and universities, both in the UK and internationally. And the business is sort of established and has at its core a series of values, as all modern organizations do, and these values were created by all of the people at Mpl. And we like to describe ourselves as an exemplary, and try to aspire to be an exemplary national laboratory, doing excellent science and engineering and achieving extraordinary impact. And that extraordinary impact is something that we very keen to present, because it's not only the joy and the pleasure of doing science and being, a physicist or an engineer or any kind of worker in the science and technology sphere, but how that changes people's lives. And we have a specific model for doing that. Because we're a government organisation, we look at some of the really big challenges that we face and try and understand those from the point of view of measurement science and see how measurement science can have an impact on that. And so we drill down through this V diagram, as we call it, to understand that. We develop in partnership through collaborations, some very innovative and relevant solutions to these problems, and then apply them and then go back up the other side of the V to ensure that they really create some significant impact and benefit to our society and to the people in the UK and beyond. And to highlight this, I'll just cover some of the things that we're really keen to work on. So I'll give a couple of examples of some of the very big projects that we're working on. So in the top left-hand corner, you can see a satellite looking down on planet Earth, and we're involved in a program called Truths, which is a new mission that we're launching in collaboration with the European Space Agency and a number of other partners. And this is to develop a new way of measuring, or new and highly accurate ways of measuring surface temperature on the planet to ensure that we can develop better models and validate climate change problems that we have at the moment. And hopefully that will help to really determine, what are the things that are making a big difference to climate change and helping advance in those areas. In the bottom left-hand corner, you can see a LINAC, which is used for cancer treatment. And the kind of work that we do at Mpl is very significant in ensuring things like the dose of the radiation that's delivered is absolutely suited to the target treatment and minimizes the damage to the patient. So, these are key areas where physicists in particular have a very significant role to play in keeping the nation healthy, or at least helping to cure very significant diseases that trouble us. And so I think there's around 5,000 physicists working in the NHS today, ensuring the delivery of the best healthcare, particularly in nuclear medicine. And in the bottom right-hand corner, there's a sort of a picture of a fuzzy nighttime scene of somebody driving, and measurement plays a very, very critical role in ensuring that, say, for example, on autonomous vehicles and the implementation of autonomous vehicles, because the world is fuzzy, difficult, and quite hard to understand, and precise and validated measurements are absolutely critical to that. So physicists, engineers are really key in ensuring that the right science and technology can be developed and then applied into these spheres to make things work for the benefit of humankind and a number of other areas, commerce and trade and so on. So that's just a sort of potted series of examples of where Mpl has some activities and has a great deal of impact in doing that. And I'll mention a couple of those things as well, because that's currently what we do, but it's based on a relatively long history for a modern science and engineering organization. Now, measurement and the need for standards goes back some way, but certainly in Britain, to Magna Carta, where they were very keen to ensure that measurements of wine and ale, so clearly those preoccupations were the same then as they are now, and food as well, and so that was enshrined in certain documentation and ensured that there was fairness around trade and exchange of goods. And many hundreds of years later, through the sort of work that a number of European nations did together, the Meter Convention was established in 1875 on the 20th of May, which is now celebrated as World Metrology Day every year. And that's the framework for the global system of measurements, which you know as the SI system of units, the Système International. So based on that and those activities, Mpl went on to become established in 1900 and was officially opened in 1902 at Bushey House in southwest London, in Teddington. And the photograph that you can see there is of the Prince of Wales inaugurating the building and the institution. And the key thing about what we are, and what I've been saying is that Mpl has always been established to play a significant role in not just international measurement and and ensuring that we can do that accurately and well, but also to break down the barriers between scientific theory and practice. And that's where, physicists, chemists, biologists, engineers all have a part to play. And, we continue to do that and really drive forward with our partners, and particularly our academic partners and our industrial partners. We bring together a variety of know-how and a set of needs that hopefully makes a big and positive change to the world. So that's where everybody who's hopefully attending this conference, whether you're a PhD student or a supervisor or a scientist, we can make a big difference, and a positive one at that. So a couple of notable achievements, just to set out some sort of key milestones along the way, and these are all sort of in the middle third of the 20th century, which is clearly a bit of a golden age for a number of institutions. In 1946, there was the world's first automatic computing engine, ACE, which was worked on by Alan Turing, and so there's a strong link there between Mpl and BT, or GPO as it was then, and Tommy Flowers himself, who was also a collaborator of Alan Turing's, and made the actual equipment that delivered these early computing capabilities. The invention of radar just before the Second World War as well was there was some instrumental work done, field work done at Mpl to help progress that and give Britain a significant advantage in that period. And then later on, packet switching was developed in the 60s, and that's a technology that we know and rely on now as critical to enable the internet and ensuring that information can be transferred efficiently across large networks, and certainly was the start of something very useful then. And I've left the last one from 1955 to last because it's probably the single most important thing that was developed at Mpl during the 20th century, and it's the world's first cesium atomic clock, which significantly improved the accuracy of timing. Now it's increased and improved by some orders of magnitude. In fact, that optical atomic clocks are accurate to 1 second in the life of the universe, and that's something that is instrumental in ensuring that we have the most accurate GPS, for example, and we're able to synchronize networks and other types of activity across very large spaces and over large distances. And that's obviously critical to much of the work that's done by organizations like BT and similar. So that's a sort of romp through Mpl. Normally that presentation's about 50 slides long, so I thought I'd spare you that and just try and pick out some of the really big highlights. And now I'm going to move on to the PGI, the Postgraduate Institute for Measurement Science. So a lot of people ask what it is, and I think the best way to describe it is very similar to Tommy Flowers Network. We're a virtual institute for research and training, but we focus on measurement science and where measurement science can have an impact. But what's critical to what we do is that our projects are very much aligned to those important measurement challenges, which I outlined in our V diagram. So we're really keen to ensure that the work that we do has that kind of purpose. And I know that BT has a strap line, BT Research, a purposeful innovation, and we concur very much with that ethos as well. And one of the ways in which we can get the best knowledge to be translated into the most useful outcomes is by connecting industry and academia. And I think these are things that the Postgraduate Institute and Tommy Flowers Network and many organizations who support postgraduate research have at their heart. And it's really critical that we work towards achieving that as we go through 21st century and try and solve some of the very significant challenges that we face over the next few decades. So our key activities are obviously research, as I mentioned, but as I say, it's research with a purpose, with a measurement science underpinning, and also one that's connected to our sort of academic industrial complex across both the UK and overseas. So we're not parochial, we are an international organisation. And the SI is rather interesting in that it is probably the only thing that humanity has ever truly agreed upon without argument. And even during times of international conflict, during the world wars, the SI was still maintained through collaborations and communications between national measurement institutes. So it's a guiding light, I think, to all of us, but also that science and engineering is a way that we can bring people together, irrespective of what other differences they have. One of the things that we like to do, and I know that many institutions want to enable our postgraduates through training, for example, and that's critical. And just to open up the opportunities, particularly we like to think of the experience of doing a PhD in collaboration with Mpl and other industrial institutions as one that will broaden the horizons for students engaging in a life or a career in science and engineering. And that's something that we get some very positive feedback on as our alumni move on into their careers. And they know that having had that experience, it significantly benefits them in ways that are slightly intangible, but definitely beneficial. And of course, we have a really strong push and desire to ensure that there is a good cohort experience. So I mentioned earlier in passing that we have around 200 PhD students that are co-supervised at Mpl, and bringing them together in conferences, whether online or in person, just like the Tommy Flowers Network is doing and has done, very consistently and repeatedly, frequently, in fact, over the past few years, is a way to connect people, to get people from different areas to understand each other and to share problems and solutions, and that's critical. We need to maintain that activity, and it enables a much bigger sense of what we're doing and the purpose, but also the outcomes and the benefits. So we're very happy to see people from different fields that they're all physicists but working in very different fields and different applications come together and talk about the things that they do in a very sort of excited and energetic way. So and I probably have to say that why have I done this way? So I'd like to just mention that the partnership. I mentioned earlier that Mpl in 2015 had a sort of change in its operating model, being government-owned and government-operated from previously being company-operated, and it was as a result of the partnership with the universities of Strathclyde and Surrey that Mpl then had to develop a postgraduate institute, and that's particularly important. And the reason why I did it this way around is that I wanted to focus much more on what impact the PGI has on postgraduate students. But underpinning that is this fantastic partnership, and the two universities that I've mentioned there have a very strong ethos of translating academic know-how into industrial and third-party user benefit. So there's a very strong connection between the academic institutions and their surrounding industries and public organizations, particularly healthcare, for example, in the case of Surrey, and with some of the big institutions in photonics and also manufacturing and energy supply up in Scotland. That said, I mentioned also that we're celebrating 5 years, and one of the ways I wanted to just put across how important it has been to bring together people and hopefully inspire them to do things and connect more. And hopefully there is some sense you're getting that Tommy Flowers, for example, and PGI and other institutions are really there to bring these ideas together and the resources together to support interesting and fulfilling, meaningful careers for physicists and scientists and engineers of all shapes and sizes. And over the last 5 years, we've had a tremendous growth in the number of students that we've been supporting. So about 82% rise in sort of the 5 years. We've also seen 140 PhD students graduate. So there's some real kind of momentum going now, and in that time we've really picked up on a couple of key things that we know can help to ensure we are doing the best job possible for our scientists and supervisors and the institutions that we partner with. So one of those things has been to develop something called the Supervision Charter, and this is a way to improve the student supervisor experience by setting out very clearly what the contract is, in inverted commas, between the student and the supervisor, and developing that professional, kind of career-minded role and activity as you sort of transition from undergraduate to graduate studies and beyond. And in that time as well, we've been working with a lot of industrial institutions to ensure that we draw in funding and support from those institutions so that they may benefit from people who have these high-level skills, who can develop and innovate in ways that are significantly greater than would be possible without having that sort of deeper understanding of the science, the engineering, the physics underneath all of these complex phenomena that exist in the world today, and that we're trying to exploit to develop new technologies and new activities. And I'd like to say, like Fraser was saying earlier, we've benefited. We've had this great benefit of the pandemic, which has been that our conference this year had I think it was a 30% rise in attendance due to it being online. So we were able to bring people in from across the world as well. So, saying good morning, good afternoon, and good evening at the beginning of every one of our sessions, which I think is very different to what we'd experienced before, but quite pleasing that we've pulled out some really interesting developments and opportunities from the crisis. So that was the last 5 years. During 2020, we have produced a report of that activity. It's called our review, our 5-year review, and that's published and available for people to download to look at in more detail. And I just want to pick up a few highlights from that report as to what we've done. Again, this is sort of evidence that shows how what we're doing really has an impact in terms of ensuring that we create this broader set of horizons for people, and we're very pleased that the largest single kind of, portion of our postgraduate students go and work in industry after having done a PhD in collaboration with Mpl. And we also have people that stay at Mpl, about a fifth of them stay on, and nearly 30% go to academia and work in academia, but presumably with a very good understanding of the relationship between academia and research laboratories and industry partners. And we've highlighted here some case studies of some of our star students as they've gone off into the world and achieved great things. We also highlighted some of the fantastic publications and the recognition that our students have. So, it's very important for us to celebrate, just like Fraser mentioned, showcasing and celebrating the great talent that is developing through this period of PhD research and collaboration. So we're very happy about that. We're very proud of our students. It's becoming a family in some senses, and we are connecting much more with them to create this kind of longer term relationship, and hopefully, as time goes by, there'll be some significant benefit of having brought together people and collaborated in this way. In terms of the demographic as well, we have a very broad spectrum of people that do research as part of the Postgraduate Institute. So around 60% UK and 40% international or EU, and that reflects the sort of demographic that we have at Mpl. We're also happy to report that we've got a good gender balance, and particularly good for physical sciences. It's slightly better than the national average, which is 31% female to 69% male. We try very hard to ensure that we are providing opportunities that are lowering the barriers to career in science, particularly in physics and engineering, where they are traditionally dominated, male-dominated areas. Anyway, you can read all about that sort of thing in our report. There's a DOI there for you for anyone who's interested, and can circulate that later. So, and finally, I just again want to mention how important it is for us to communicate and celebrate what our postgraduate students do. And again, chiming very strongly with what Fraser's saying, and what Carol is doing, giving out prizes because we value the contributions and we think that what people are doing is truly excellent. And we have a publication, our quarterly publication, where we talk about all the things that our students are doing. And this is a publication that's led and edited by our students. I forgot to mention actually that our annual conference is always organised by our students. So it's tremendous that they get so involved, and they always come out of it with smiles on their faces, even though there are some grimaces with all the challenges of having to organise something in lockdown and with very different approaches. And in the most recent copy of the grad post, we talked about how our students were helping combat the COVID-19 pandemic, using what skills they had, and particularly one of our students at Huddersfield, and helped by a student at Surrey University, were using 3D printing techniques to make face shields. And we talk about what impact lockdown has had on us, and share our experiences and develop different sort of training, mentoring schemes, and other events to ensure good communication across a very broad range of both technical and non-technical topics. And the final kind of photo there, or image there, is about our 5th annual conference, which was held last month in a slightly different format, but very similar in the sense that we had it spread over 4 days, short periods, and also a day where we really focus on specific activities around what the students were doing. And ours was thematically based, very much like the TFN conference today. And very, very positive feedback came from our students for that, because it gave them that opportunity to show how their careers are developing and how their science is having a significant impact on the other activities that they're working on with Mpl. So that's everything about the PGI. I hope it's given you a good sense of what we do and why we do it, and how there are tremendous opportunities out there, and lots of rich and interesting careers across the board, that result from having a PhD in physics, and where physics can have a really big impact on our lives, both in terms of quality but also safety and security. So I don't know if there are opportunities for questions or time, but thank you very much for listening. I hope you have been listening, and I'm happy to take any questions either now, or if you want to transmit them through the Tommy Flowers network. There's some ways of getting in touch. So please do get in touch. This is a collaborative effort, and we're really open to any kind of interactions and new relationships. So thank you very much.
Great. Richard, thank you very much. We probably do have time for one, possibly two questions. So it has one on the previous events. If you guys want to pop something in the Q&A, if you want to ask a question of Richard, but I'll pose one now for the moment. Richard, what's your biggest challenging in finding the right people with the right skill sets at the moment?
Well, it's interesting that you say that finding the right people with the right skill sets. We don't worry too much about that, because partly what we're about is ensuring that we can develop people with the right skill set. So we've made a lot of effort in trying to understand not just what our students want, but also what our industrial partners want. So that the model that we have of this, it's quite immersive PhD training. So it's not just about going and attending courses, but the fact that they are in a lab, potentially day to day, a working lab, they learn a tremendous amount, and it really helps in that transition towards a career in a working lab. You have to operate as a professional working scientist, even sort of from day one when you're collaborating with us. So, the skills are important, but, we have tremendous universities, tremendously talented, wonderfully bright, I don't want to say young people, but just generally they are, coming through, the education system. And so, yeah, we're spoiled for choice, but we try and do something significant to help broaden that horizon by the breadth and the type of training that we do.
Cool. And do with the people that do apply and participate, do you see a typical background, or is it kind of wide and mixed and varied in terms of the people that kind of apply?
Well, we do have a typical background, and primarily, they are physicists, engineers, chemists, biologists, and so on. And so, yes, they have a science and engineering background. But one of the things that we're working on at the moment is trying to broaden that participation and looking at ways in which we can bring, the opportunities to people who are not going through traditional routes. So that's very important to us because, as we want to grow the number of researchers in the UK, there's some big challenges that we have to meet. We need to fish in a bigger pond, and there are some very bright people who may have left school or left university without the idea of wanting to do a higher degree, but after 10 or 15 years of working have got such talent and energy to develop further that there needs to be more opportunity for them to develop in that particular way. Okay, great, Richard. Thank you very much. I'll bring nobody's posting any questions, so I'll bring that session to a close. If we get any others, we'll pass those. We'll pass those on to you. Thank you. Great. Thank you very much. Right. So we're about to move on to our next session, where we're going to get into the lightning talks. We've got 6 5-minute presentations, and just so everybody is aware, I do have a stopwatch. It's not a cesium standard, as was discussed earlier by Richard, but I do have a stopwatch, and I will stop each presenter after they've had their 5 minutes. If you had a look at the agenda, we've had a slight change in order. Unfortunately, Edward Alston could not make it today. He's having to deal with some family issues, so our thoughts go out to him today from that perspective. So we're moving one ahead, and we've got a slight change in order as well, but you'll see how all of this makes sense as we work through the next series of presentations. I do want to mention one thing. This is a very eclectic and mixed group of not only topics, but people. And I'm going to pose a challenge to those of you that are just listening to the presentations before I hand over to the first presenter. And that I'd ask a number of them something really, fascinating or interesting about their background. And I got slightly surprised, which I always do when I ask these questions. So one of our presenters out of the next 6 was actually a performer in the 2012 Olympic opening ceremony. They were a drummer.
in the Industrial Revolution part called Pandemonium, for those of you who remember that. I actually went back and looked at the video clip of it. It was quite fascinating. So I'm going to ask you to try, if you want to have a go, have a guess who you, once you've seen all the presenters, who you think that may have been. We've also got another one of our presenters who is a actually classically trained pianist. I'm not going to give the rest of it away because it kind of give away who it was at that point. And then we have another presenter who had taught 10-year-olds to code in Python to run on a Raspberry Pi to actually give you warnings around temperatures, whether it was hot and cold, and ended up on the International Space Station, which I thought was quite fascinating as well. So as you can see, a real mix here. So what we'll do is we'll get into the first lightning talk. So I'd like to introduce Frank Carver from the University of Suffolk, educating future software developers about sustainability. So Frank, over to you.
Thanks, Mike. I hope everybody can hear me. Right, so I'm, well, I've done about over 25 years in the software business, and during that time, I got kind of upset about certain aspects of the business. So what I've done is I've taken some time out to do a PhD at the University of Suffolk. Now I'm dealing with, my broad area is sustainability of software development. So in order to introduce that, here's a bit of background. So most people tend to think of, if they think of it at all, think of the cloud and the internet as being essentially free. But that's not the case at all. Some recent estimates, 2019 estimates, reckon that the carbon output of the internet and data centers in particular is approximately equivalent to that of the entire airline industry. Now, that's a massive amount. Data centers in particular, they contribute, or they use up about 1 to 2% of all the power generated in our country. And an even bolder estimate has also come out recently saying that the internet as a whole takes about 10% of the world's electricity. Now, this is a big figure, so it seems to me that there are some improvements that could be made, but it gets worse than this. Because when you look at the electricity generating process, if you take the energy in the fuel that goes into power stations, then most of that, 80% or so, is lost before it even gets to the servers in the data centers. So it's lost in the generation process, it's lost in cabling, it's lost in lighting and cooling and backup power, and all sorts of things in the process. So you've already lost about 80% of it. And then when you actually look inside the servers, then you get to more losses. Essentially, servers have their own power supplies, which lose power. They have their own spinning fans and spinning disks. And at any given time, most of them are probably not doing as much as they ought to be. So as a rule of thumb, you're probably looking about 1% of the generated fuel, the fuel fed into the generators, is actually being used to power actual software that we actually want to use. Now, this is a big issue because there are about 100 million servers on the internet at the minute, and software efficiency therefore matters. So if we want to solve this problem, if we want to improve the sustainability and efficiency of systems, we need two things. And one of them is about education. However, if you've been through any kind of computer science education, you'll probably come across some of these efficiency things, big O notation and comparing algorithms and all sorts of things. But there are problems with the way this is taught. So apart from anything else, we tend to teach software development by saying, well, you'll start with a blank page and you'll be given a problem, and it's probably a fairly standard problem, that there's textbooks about it. But the biggest problem is that essentially, if it won't fit on a PowerPoint slide, then we don't include it in the lectures. And real world problems are a lot bigger than that. So in the real world, we don't start from a blank page. We don't start from an empty text editor. What we do is we look at a bigger problem that there might already be a code base, but certainly when we're trying to make things work, we look for already existing components and libraries. So they come from any or all of these sort of places, and the great majority of components that we use in our modern software systems are free, in the sense that they're free to buy. There's no monetary cost. However, we don't really know anything about them. So I took an example component thing and did some comparisons. So if you think a little bit about a typical web page, okay, so you go to a website, you fetch the web page and you get a bunch of text, and it's probably customized with all sorts of different things. Now, it's a long time since anybody sat down with an empty text editor and actually typed in a web page. These things are all generated using what's called templating, where most of it exists and the gaps are filled in dynamically when you request the page. Now, I compared a representative example of these libraries to do this and found there was over 1,000 times difference in performance between the best and the worst. So to put that into context, if you're filling up your servers, then you might need 1,000 times more servers to serve a particular application if you chose the worst one out of this collection than the best one. And so it's 1,000 servers instead of just one server, and that makes a huge difference. So there's a big problem to be dealt with here because we can't work this out. There's no information. So if you compare software with the way the rest of the world works, well, we're deluged with information. If you buy a home appliance, it comes with an energy rating. If you buy an electronic component, it comes with a data sheet. If you buy a car, it comes with miles per gallon figures, and people argue about how accurate they are. In software, well, it kind of works. That'll do. Move on to the next project. We don't really consider any of this stuff. Now, obviously, there's an issue with the documentation here, but there's also an issue with education. Young software developers, new software developers are not taught any of this stuff. Now, sustainability is beginning to become an issue. So all of these different accreditation bodies that I'm showing on here, they all have sustainability now in their
Frank, yeah? Frank, I'm going to have to stop you there. That's 5 minutes, mate.
Man, let me get to the last slide.
Okay.
If you're one of these people, please get in touch. And my slide deck's available at the address given.
Apologies. That's a lot of information to cram in 5 minutes. So thank you very much. Right. Our next presenter is I knew I was going to do this. Katja Chatso, University of Essex, Political Text Classification using Neural Networks. So, Katja, are you with us?
I am. Oh, bear with me. Starting the video as well. Thank you very much, everybody.
Right.
It's lovely to be amongst everybody's company and to have the opportunity to present some of my recent work that is trying to bring together some of the technologies used in computer science and engineering, such as deep learning and neural networks, but using them for social science. So the kind of main two research questions I have been trying to address with this work are around, first of all, whether the choice of word embedding for a sentence topic classification with convolutional neural networks, a type of neural network, can improve your accuracy if we apply it to political text, but also for political text, whether we could port what we've already done, training, the hard work of training these neural networks, classifier across different discourse styles. So what I'm doing is I'm applying what my training set already knows to a test data set of COVID-19 press briefings that I have been collecting since March. And I'm doing similar comparisons. There has been quite a lot of work, both so for political science, that the use of these methods, of these computer science and deep learning methods, is fairly new to some extent, especially the unsupervised ones. And there has been some work around domain transfer of political manifestos of classification to other political texts. So this is not completely new, but it's sort of there are it's one of the few pieces of work that are using that at the moment. So the two data sets I have used was the Manifestos Projects Corpus. So for those of you that might know anything about political science, this is a very famous one where expert political scientists have manually annotated political manifestos of political parties. And what they do is they use seven larger classes and 56 smaller ones. So the larger ones, the domains 1 to 7, are shown in table 1 here on the left. And what I have picked for my experiments is the English subset of the 115 manifestos, which is approximately 86,000 annotated sentences. For the kind of the second part of the experiment or the research question, the COVID-19 press briefing corpus, as I said, this is something that I have been putting together since March. It includes the press briefings that governments usually do for COVID. At the moment, they are approximately 62,000 sentences it includes, and I have selected a sample of that, of 20 of them, about 1,700 sentences, and which were manually annotated by two political scientists. The architecture I have used is shown here, but in the interest of time, I'm going to move quickly to the next one, which shows the findings. In the first question, does the choice of word embedding for topic classification as applied to political text, does it improve it? We see that experiment 4, M4, which includes the neural network with the latest word embeddings, shows a lot of accuracy and improvement there. Whereas for the second one, we see, the second research question, we see that it is possible to port this trained classifier across the different discourse styles, but there has been a loss of accuracy as expected because the domain is slightly different. So just to sort of summarize what's happened here, so we built a sentence-level political discourse classifier. We used the existing human expert annotated corpora of English political manifestos, the Manifestos project, as I mentioned. Then we tested the accuracy and performance of a convolutional neural networks classifier using the different word embeddings. And we showed that out of the different combinations of experiments, the convolutional neural networks plus the BERT word embeddings outperforms the others. And finally, we took that one step further to answer our second question, which is to apply the same pre-trained models to a different type of political discourse type, so the COVID-19 press briefings, with no additional training, and we saw the difference, slight difference, well, actually quite a lot of difference in the accuracy being dropped. So in terms of the next steps, I hope to be conducting similar experiments with 56 subdomain manifestos classes and other types of neural networks to see how they perform, and also experiment with different languages in the manifestos corpus. And what I forgot to say is that I am a senior research officer in a research institute at the University of Essex called the ESRC Business and Local Government Data Research Centre. And with that note, I'd like to thank you and hopefully we can ask some questions towards the end.
So Kathy, thank you. I was just about to say, it's time to stop. You was only 4 seconds out. That was amazing. Great. No,
thank you. I'm sort of doing that as well. Thanks.
Great. Thank you very much. Right. Slight change in order. So our next presenter is Yiton Lin from University of East Anglia, typically plausible spectral reconstruction. So Yiton, over to you.
Thank you, Mike. My name is Lin Yidong, and I'm a second-year PhD student at the University of East Anglia. Today, the topic I'm going to talk about. Sorry.
Yeah, if we just start again, because I'm just trying to get the ball down to you at the bottom of the list. Hang on.
Right.
I'm just going to move. Oh.
So the timer is going to restart.
No. You're fine. You're fine.
Now, I'll restart it. That's not a problem.
Yeah.
I can't get down to people. Oh, hang on. Because you're at the bottom of the list, my screen's not big enough. Apologies, everybody.
Just let me know when you're ready, Sarah.
Yeah. There we go, Lynn.
Okay. Cool. I can move my slide now. Okay. So my name is Lin Yidong. I'm a second-year PhD student, as I said before, at the University of East Anglia. And today the topic I'm going to present is physically plausible spectral reconstruction. So in spectral reconstruction, we'll try to get the radiance or spectral information from only the RGB or color information. And most of the time, this is formulated by machine learning algorithm. And in this study, we tried to examine the physical plausibility of those algorithms, which means like whether or not the predicted radiance is going to adhere the physics between the actual radiance and the color. So why do we measure spectrum? As I show in the example on the right, 3 different objects having the same color appear to have very different spectral characteristics. So in terms of computer vision, this means that we can get the material properties at pixel level. And in terms of computer graphics, this means that we can use spectral imaging to characterize the object surfaces so that we can predict their colors under different illuminations. However, the recent technology has many drawbacks. So we want to reconstruct the radiance spectra using only the RGB data. So people from the machine learning study may tell you that this is very simple. You just give me a lot of matching color and spectral data, and I can train a model which does the job. Some recent methods like deep learning, deep neural network, or convolutional neural network is really complicated inside, so people refer them to a black box. You don't know what's actually happening inside, but it gives you the final answer. The problem here is like when we are training those black box solutions, we often forgot the simple relation between the radiance spectra and the color. So in an RGB camera, we have 3 different types of color sensors. Each can be described as spectrally varying sensitivity functions. So the colors are actually the weighted sum of the radiance spectra using those set of 3 spectral sensitivities. So we designed a very simple testing experiment. So from the ground truth RGB image, we recover the estimated spectra using the black box solution, and then we reapply the spectral sensitivities to see whether or not it reproduces the actual RGB image. The result is not quite. So the leading deep learning model gives us very significant color shifts. So if we think about the application in computer graphics, especially in artwork conservation, we wouldn't want to use the model which shift the color. So the problem here is like how we're going to make the existing model physically plausible. In a nutshell, our approach is to open 3 dimensions of the black box. We can represent the radiance spectra as n unknown points because we're studying spectral reconstruction, so those discrete spectrum are unknown. And these spectral sensitivities can act as the model coefficients, which gives us a physical system, which is the 3-equation linear constraint. We want to make use of these constraints in the spectral reconstruction process. Well, sorry about the math. Here, we can represent the linear system as y equals A transpose X, where X is the spectrum and Y is the color. With respect to this coefficient metric A, we can split the spectrum into 2 components, one spanned by the column space of A, the other part lies in null space of A, here I denote it as B. So what we need to know is like this A and B metrics are orthogonal. So using those information, we can essentially open the 3 dimensions of the box. Why? Here we see like the coefficient A can be calculated directly using the RGB and the coefficient metrics. And whereas the coefficient B, we just rely on the machine learning techniques help us to figure out. So, using this model, we show that our methods preserve the color validity during the spectral reconstruction process, and we advance the spectral accuracy of the state-of-the-art model. So this concludes my presentation today. I hope you enjoyed the talk. Thanks for listening.
Great. You caught me off guard there. You finished early. Great. No, thank you very much. Right. We'll move on to our next presenter, Daniel O'Connor. He's going to be from UCL. He's going to be covering quantum annealing for network optimization. So, Daniel, over to you.
Brilliant. Thank you, Mike. So today I'm going to talk about what I'm researching in my PhD, and that primarily concerns quantum annealing for network optimization. So some of the hardest problems in computer science are concerned with discrete optimization. For example, we have the traveling salesman problem on the left here, where we have a set of points and we want to find the shortest path that visits all of the points. And this problem normally has a cost function associated with it, and here the cost is obviously distance, and we get some landscape as we can see here on the right. So, and our best possible route we can take is the minimum or the global minimum indicated by the star there. But typically, modern day algorithms tend to find something close, a local minima, that's not quite optimal, but is still good enough approximation nonetheless. But obviously, if we can use another method that can find the optimal, we can find a better solution, as you can see here on the right. And to be able to get to that better solution, we need to be able to traverse this landscape and maybe jump over the barrier. Maybe some of you are familiar with simulated annealing, where we use thermal activation to traverse this landscape and get to better solutions. But in quantum annealing, what we use is something called, we use quantum tunneling to traverse the landscape instead. And how this protocol basically works is that we start from a simple quantum state, which we can see there on the left of a very easy to determine space, And what we do is we anneal from the quantum state to the classical system, and therefore we should end up in the ground state of the system at the end of the anneal. What this actually looks like in real life is a bunch of quantum spins, or qubits for short, which are in a superposition of all possible classical states. And because they can see every possible classical state, and when we slowly anneal, we should end up in the ground state at the end of the anneal as well. The current state of the art is run by a company called D-Wave Systems. They have over 5,600 quantum spins or qubits in their quantum processing units. And an example is shown on the left here with their Pegasus architecture with only 264 qubits, so you can imagine what 5,600 looks like. And using hybrid methods such as classical optimization methods like taboo searches, with quantum annealing, you can solve problems of up to 1 million variables, which is quite an impressive amount. So why quantum annealing in general? You get more qubits than any other noisy intermediate quantum system. D-Wave annealers only consume 25 kilowatts, which is obviously interesting considering Frank's talk earlier, which it's a lot lower than, say, these data centers and supercomputers, which consume on the order of megawatts. And it's also can be applied to a range of problems in optimization, machine learning, and materials science. And with networks specifically, it's been applied to job scheduling problems and also large-scale MIMO processing as well. The con to this is that it's not a universal form of computation, such as a universal quantum computer using gate-based methods. There is an undetermined speed up, and there's hardware constraints because qubits can only see so many other nearby qubits. So what we do at UCL is that we look at to explore the physics of quantum annealers. We have our own qubits, which we run experiments on. But what I'm primarily concerned with is obviously more of the theoretical side of things and experimenting with the D-Wave as well. So what we've done, as an example of what we've been doing in our work here, is we've got a cost landscape here where we've got the same barrier heights, and our local minima on the left and right have different distances to our ground states. So we can thermally activate the same from each direction, but it should be harder to get from one well to the other well in this landscape using quantum tunneling. And how we can do this is that we can start on these local minima by using something called reverse annealing, where we start in a predefined initial states. And what we do is we induce some quantum fluctuations by some amount, which can induce tunneling, and such that we can reach the ground state again, which is kind of attributed to a kind of a local search mechanism. And so what we can do is that we can start in these wells, we can see on the left, and we can run this on the D-Wave. And what we can see is that as we get different results. So what we've got on our results on the right there, along the y-axis, we've got probability of reaching this ground state against the magnitude of quantum fluctuations induced into this kind of problem that we're applying. And we can see that basically the closer you are to the ground state, the higher probability you have, and it's ordered consecutively as well, which is very nice. The mechanism behind this is still being explored, but it's something that's of great interest to us. So in summary, quantum annealing can be used to solve discrete optimization problems, and it's readily applied to network problems such as MIMO processing, and there's ongoing work for approvable quantum speedup.
Right. Thank you, Daniel. Once again, pretty much on time. And I've learned a new word today, quantumness.
Yeah.
I'm going to roll that one out in my next conversation at the pub, just to see how that goes. Right. Thank you for that. Right. Our next presenter is Hannah Steventon from University of Suffolk. Smarter Suffolk, Sensors and Data for Public Services. So, Hannah, over to you.
Thank you, Mike. Hi, I'm Hannah Steventon, and I'm a research associate at the University of Suffolk, working with Suffolk County Council and other exciting project partners on the Smarter Suffolk project. The Smarter Suffolk project is led by Suffolk County Council and is developing a county-wide network of hundreds of Internet of Things sensors supported by the street lighting infrastructure. So these include monitoring for road usage, road surface temperature, which is useful when we decide whether to do winter gritting, air quality, bin fill levels, and other things. We aim to improve the targeting of street lighting, of winter gritting, and of other services. Where necessary, these sensors use the power connection that's provided for the street lights, but some are battery powered using low power wide area networks to run for many years from small batteries. Some are trialing renewable wind and solar power. They use a range of different communications technology, including mobile cellular, LP1, including Suffolk County Council's own LoRaWAN network, or the communications networks that exist to operate the street lights. Big data presents challenges across the 4 V's: volume, velocity, variety, veracity. The sensors deployed across Suffolk at the moment are returning, the new sensors deployed across Suffolk are returning data in some cases every few seconds, often minute by minute data where previously only monthly totals have been recorded. This is a high volume of data from multiple different data sources, building data sets of millions of points, like tens of millions of data points covering traffic in Ipswich, hundreds of millions representing temperature and weather across Suffolk. Data arriving from multiple sensors and suppliers in different formats via different routes. So our BT colleagues on the project are constructing a unifying vendor-agnostic data exchange, which will simplify data formatting and access. The data is covering different technical themes, so air pollution, information for winter gritting and gully cleansing, and so the decision making that's based on that data, it varies across a wide range of legislative and business drivers, so how the data becomes action varies quite a lot. To compare data from different sensors, we've set up a number of different sensors in the same location, running at a test bed at BT's Research and Development Campus at Adastral Park, which is where we would be today if we were there in person. The lighting columns here are carrying multiple items. You can see this in the photograph. We see 3 road temperature sensors in the photo. There's another 2 at the foot of this lighting column. These sensors vary in price from hundreds of pounds to thousands of pounds. So the question becomes, are the cheaper ones as effective? Both these are battery powers, one uses lighting column power. The acquired data arrives in consistently formatting, so data cleansing has been interesting. An initial comparison of the data reveals that they follow the same variability, but then accuracy can be challenging. And other challenges that we can see in the plot here include reliability of developmental hardware. A key question here is how we apply the data as action. Over 2,000 miles of Suffolk roads are gritted, and these decisions are based on forecasts rather than nowcasts. One area where data formatting data use has been working well is in street lighting. At the beginning of the year, I typically share this data from traffic counting in Ipswich from last autumn, which shows traffic counts on a road in Ipswich across different days. The very strong blue lines indicate days on which we had football matches at Ipswich Town Football Ground, and so dynamically adaptive lighting based on traffic counting was able to take into account the increased traffic from the football matches. I feel this data is rather last decade, with football matches, with people watching them in person, and we've all seen national time series of vehicle movement changes during the COVID-related lockdown of the last few months. So here's mine, showing changes in road usage, but only at night time over the past year. So focusing on street lighting use, this is nighttime vehicle counts, showing how the dynamically adaptive street lighting can adapt to the unexpected decrease that we've seen in road usage over the last year. And this has financial and environmental benefits that have been able to be applied straight away. This project has a wide range of exciting project partners that we're really pleased to be working with, and has been funded by Adept Live Labs programme to Suffolk County Council. Thank you very much for listening. And I think I'm just in time, Mike.
You won the prize for timeliness. Thank you. That's within 0.21 seconds. Right. So we've got one more lightning talk, and it's from Eleanor Crane, and we're waiting for the presentation to come up. And Eleanor's going to talk is from UCL, and she's going to talk about 2-qubit entangling gates to quantum algorithms and the steps in between. So are you ready?
Hi, thank you for giving me the opportunity to give a lightning talk. My name is Eleanor Crane. and I'm a fourth-year PhD student at University College London, where I work on quantum computer hardware, and I also have more recently been working on quantum computer software with IBM. I'd like to give you some context before telling you about my research, where we propose an entangling gate, which does a 2 quantum bit entangling gate, which does not require precise fabrication techniques like the current ones do, and which has a higher probability of success and which requires less tuning. Why do we care about quantum computers? Well, there's a lot of quantum chemistry simulations which enable us to find new materials for batteries, carbon capture materials, efficient fertilizers, drugs, protein structures. Essentially, quantum computers have access to a different complexity class than classical computers, the bounded error quantum polynomial class, not unlike just polynomial time problems that classical computers can solve. And this enables us to optimize problems with supply chains and logistics, or related to financial portfolios. And ultimately, it enables us to understand how our universe behaves at the atomic and subatomic levels. Well, how do quantum computers, how do we use them? We use them on a classical interface, and this is the IBM Quantum Experience Circuit Composer, where anyone for free can create a quantum circuit using gates and run it on a real computer. Just a quantum computer requires gates, just like in a classical computer you have AND, OR, NOR, XOR, and so on. In a quantum computer you also require gates. And the Qiskit language is open source, and what's special about it is it's applicable to any type of quantum hardware. There's different types of quantum hardware. There's silicon, superconducting qubits, ion traps, cold atoms, you name it. There's lots of different ways of controlling quantum bits and entangling them. So how do they work, quantum computers? What's really key? What are the key items for quantum computing? Well, two of the main ones are entanglement and superposition. What is a quantum bit? How does a quantum bit make use of superposition to begin with? Well, a classical bit has 0 and 1. A quantum bit, or heads and tails, has in the superposition of 0 and 1 until you measure it and you collapse the state, and you can then only read out 0 or 1. It was tails. So you probabilistically, by making many measurements, then find out what the actual state was. In silicon, in the platform which is silicon, which is what my research is about, you can have a silicon atom, which is a black dot, connected with electrons to other silicon atoms. And if you replace the silicon atom with a phosphorus atom, it's got an extra electron compared to the other silicon ones. That extra electron has spin and can make use of, is a quantum item which can make use of superposition. What's something else which we really need for quantum computers? We also need to make use of entanglement. Entanglement is if I create an entangled state between 2 quantum spins, it's difficult to create the entangled state, which is what requires an entanglement gate, but the entanglement enables me to, if I create the state, measure one and know without looking what the other one is. However far apart I've put the other one, it doesn't matter. I know from one what the state of the other one is. So how do I make this very important gate in silicon? I can control the electron by shining light on it. And if I shine light on 2 phosphorus donor electrons at the same time, they both try to absorb the light and expand. That's fine if they're far apart, but if they're close together, they can't do that. And that is called the Rydberg blockade. This way, we correlate the electrons. We try to shine light on them, and their behavior is correlated because they can't both expand at the same time. And this entangles the electrons. And this means they only need to be within a certain distance, and they will get entangled. So using the Rydberg blockade, we've created a gate which requires less tuning and has high fidelities and is distance independent. I hope you enjoyed the introduction and that you know a bit more about why we care about quantum computers, what the different types of platforms are that we can use them on, and what the 2 core concepts are, and that we created a new type of entangling gate. I'm called Eleanor Crane, and I would really like to contact you or talk with you if you're interested to hear more or learn more.
Great, Eleanor, thank you very much. I'll move to our next presenter. So I'd like to introduce Mike Payne from Pembroke College and the Cavendish Lab. He's the professor of computational physics at the University of Cambridge. So Mike, over to you.
Okay, well, thanks very much, and thanks also for the lightning talks, which, as is so often the case, provides lots and lots of background information, which will be useful to me because it means that during my talk I won't have to say very much. And actually, just picking up on the last talk, when Eleanor succeeds in what she's doing, then everything I've done during my career in science will become instantly relevant. So useful, interesting sort of background. Anyway, what am I going to do? I've been sort of asked to give the boring old man talk at this meeting, which is to sort of look back on things I've learned during my time in science and maybe pass on some lessons. I'm not sure that any of them will be really of much use to the younger generation, but anyway, let's just see how we go. And I'm always amused when people ask me to talk about my career. You know, I tend to say, are you really serious? You want me? Yeah, no, we really want to talk about your career. And I say, okay, well, fine. But what you must understand is that when I was young, I made 3 absolutely categoric decisions, and they were, I was never going to do physics, I was never going to work with computers, and I was never going to become an academic. And as Michael just said in his introduction, I failed on every single one of those counts, up being the professor of computational physics in the University of Cambridge. And it's interesting because, you know, at the moment we get all this ridiculous rhetoric about everyone must know everything and you changed your mind and why did you, I mean, you know, young people seem to think that they need to have their whole careers fixed in place, you know, at the age of 12 or something. And, you know, all of that is absolutely ridiculous. And so, I mean, a quote that I'm sure lots of you know, but I think is very relevant is, actually, it's quite the contrary. You know, when the facts change, I change my mind. What do you do? I mean, the idea that things are fixed, that you don't change what you do because you learn more, is, of course, absolutely idiotic and yet seems to be hardwired in. There was all this fuss about the government having to change something because they found that a 1,000-page treaty interacted badly with another 1,000-page treaty, none of which people had been able to actually read in advance anyway, and they had to tweak things a little bit, and this was suddenly catastrophic. Well, it wasn't. It's because you've learned more, and only an idiot would carry on heading into a brick wall if you suddenly found out that there's a brick wall ahead of you. And yet, this does seem to be the mantra of the moment, and it is really quite depressing and completely and utterly unscientific. And of course, although it says facts here, what we're really talking about is information. Yes, you learn more. Sometimes you only find out relevant information when you begin to do things. You know, I'm sure, you know, all your whole audience of postgraduate students, you know, thought that they would learn everything about their subject area and then start doing research. Well, if you do that, you know, you'll reach about 100 and die and still not learn everything about your subject area. If you're doing research, as you know, you've got to just launch in and see where you go and keep making the best decision at each point as you go through. Interesting, when I was putting together this talk, I thought I'd better, you know, find out who actually came up with that quote in the first instance. And if you're interested, there is actually this web page, and it's not clear who actually said that thing first. There are numerous people suggested. Probably none of them did actually say it. So it may just be made up, but popular sayings are very useful guidance for everything that we do. So, yeah, I mean, I changed my mind in many ways, as you've seen already, from, you know, not going to do any of the things I've ended up doing. And, you know, I want to sort of say a little bit about what I've done. But I'm not going to go into any sort of detail. So it will be very, very high level. My email was at the beginning. If you want to get in contact with me and ask about any of the details, I'd be more than happy to do that. But that would be a very long talk and also of very little interest and relevance to most of the audience. But what I've actually ended up doing is, well, we've just heard of it, quantumness, doing quantum mechanical simulations. And so what I really want to do is just next few slides, next few minutes, is just to explain what that means, what we're doing, and perhaps a little bit of motivation of why one would want to do it. So why, well, now we're going to, so to try and position what I do, I mean, so I work in modeling and simulation, okay? And my favorite example, if you're trying to motivate modeling, is actually the example of car crash testing, okay? So unfortunately, we're not in a situation where you can actually sort of vote or phone a friend or do anything like that. But, you know, just imagine you're actually sort of doing this and voting on each of these, right? Let me ask you a simple question. How much does it cost to do a single physical car crash test when you're developing a new car? Okay, so I've got a range of suggestions there. If you feel that none of those are appropriate, you can always, in your heads, tick on a different button. But anyway, what do you think it is? And what I should warn you, I mean, people who've experienced my teaching will know that I always like to sort of draw people into the obvious answer, which is wrong as a way of illustrating things, okay? So, you know, you might sort of think, well, you know, it's a car, you know, cars are maybe, you know, £20,000, but it's a manufacturer. So, you know, maybe it's 5,000, but you might think, oh no, that's far too simple. It's got to be a lot more than that. It's sort of 50,000. Or you might think, well, I'm pushing you to 5 million. The interesting answer is that actually it's £500,000 as an estimate. And what you've got to do to understand why it is that much is to look at the question, the thing that you had drummed into you at school and at university. Read the question. We're talking about a physical, real-life car crash test. And when are we doing it? It's when we're developing the new car. Why do we do the car crash test then, rather than when we actually have developed the car? Well, if you developed a car, that costs a lot of money. It costs probably multi-millions, if not billions, to set up a physical production line in a car factory. Remember that car crash testing is a legal requirement. So you set up the production line. First car comes off the production line. If you go and do the crash test and it fails, you have to re-engineer the production line. That is another £1 billion. So in answer to that question, the trick, the thing you have to understand is that if you're developing a new car, and you have to do a physical car crash test on it, you have to hand build the car. And so the £500,000 cost of the car crash test is nothing to do with instrumentation, nothing to do with anything like that. It is the cost of hand building a car, okay? So it's a lovely example of modeling and simulation. But of course, nowadays, car companies don't have to do that. And why not? Because of the triumph of modeling and simulation. Okay, so if we go to the next slide, we find out, oh, come on, click, click, click. There we go. How much it actually costs to do a virtual crash test simulation? Well, it's about £5 now. That probably is out of date. It's probably down to £1 or £2. And, of course, you can only replace the physical test when you're developing the car by the virtual test if the virtual test exactly reproduce what a physical test does. And the picture on the left-hand side of this slide shows how faithfully computer simulations can now reproduce a real physical experiment, okay? But that was developed over many, many years, okay? You need to develop the model and the software that implements the model. You need to test it. You need big computing, and we've just heard that's a really, really bad thing, but okay. You know, against £500,000 per test, then that's probably a good thing. You need to know everything about the materials that are involved in deforming in your virtual crash test. You need to put those into the model, so you need extensive database of material properties. But develop that over many, many years, and you reach a point where the virtual simulation is as good as the real physical one. And then, of course, in the past, we've had Moore's law to help us then drive down the cost. Okay, So, right, you save a lot of money, you think that's the end of it. Actually, it's a really interesting story, because the moment it became cheap to do virtual crash test simulations, what actually happened is that the manufacturers produced cars that were safer than the legislation, because it didn't cost so much to just drag your car through the legal requirements. You could actually design ahead because it was no longer the limiting step. So that's modeling and simulation, brilliant example where it's, it actually reached fruition many, many years ago. It's a mature technology and used routinely. But going back to that last point, you need to know about the materials. So moving more to the atomistics of silicon, as we've just heard in Eleanor's talk, wouldn't it be great if you didn't have to do lots and lots of experiments on materials? You could actually just do that part of the process, predicting materials properties, just doing simulation, okay? And better still, without even doing an experiment, without even making material, without even getting the data that we've heard about over and over again that you need to then fit your model to or develop your machine learning model. And it kind of is, it's a very different type of modeling to the virtual crash testing and most other things. The idea that you go right back to what physics is all about, fundamentals from which everything follows from your fundamental equations. But remarkably, and this is where quantum mechanics actually gives you this ability, is exactly what quantum mechanics is all about. So, without going into numbers and equations, all of which are very, very, very straightforward in principle, quantum mechanics allows you to write down equations that, when solved, where the only thing that you need to know to set up those equations are the atomic numbers of the atoms in your system, or the chemical names or symbols, it doesn't matter, you just put those in. That tells you the equations, you solve the equations, and quantum mechanics is a theory that has yet to be proved to be incorrect, and from quantum mechanics we can predict all those materials or physical and chemical properties of systems. So it's brilliant because we got the equation, we don't have to develop new models for different systems, we have exactly the same set of equations, whether we're talking about silicon or window glass or a metal or whatever, and just solve the equations, you've got the properties. Brilliant. But this was known. So there's a famous quote from Paul Dirac, who of course was very involved in the early development of quantum mechanics. And he's pointed out that once you have the equations of quantum mechanics, then essentially everything is solved, because when you solve the equations, you then know most of physics, the entirety of chemistry, which of course is a trivial subset of physics, and of course biology and every other subject are then even more trivial subsets of chemistry and so on. So basically, in principle, you have the equation and we know everything about vast swathes of different scientific disciplines. Great, except the fact we can't solve the equations for the sorts of reasons that we were hearing about in the context of the traveling salesman problem, and that's something I'll get back to later on, actually. So if you look at it, it's a really funny statement, right? In principle, we know everything if we can solve the equation, but we can't solve the equation, which then, of course, raises the question of how do you know that that equation actually gives you the right answers when you haven't been able to test it? So, it's kind of like a curious thing to both claim that you know everything when actually you know nothing at all. And, of course, it is problematic, You're kind of like so close to having something really useful, but you can't get anything useful out of it. So why would it be useful? Well, this has been touched on before. So Eleanor was talking about devices and being able to use devices to generate qubits for your quantum computers. This is going back to, actually 1980s and 1990s. I've just stolen a picture out of someone's PhD thesis to illustrate these things called heterostructures. So heterostructures, this was sort of wonderful science and engineering that got going in the 1980s, where you could grow different materials, one on top of the other, and they would be perfectly matched. You could grow them without any sort of defects at all using techniques like molecular beam epitaxy and things like that. So in this picture here, we have a diagram showing a bit of gallium arsenide, then an alloy material where you have aluminium or gallium on the same site and arsenic, and then back to gallium arsenide again, and then you might put some dopants in. And this was a way of generating novel electronic structures materials with sort of particular properties that could be exploited in electronics. However, in those very early days, what wasn't known was essentially how the different electronic levels in the different materials lined up. And because it was really very important, then lots and lots of people did experiments on it. And you'd have thought, okay, well, there'd be a bit of scattered experiment, there'd be some sort of uncertainty. But, surely everyone would be getting roughly, the same sort of answer, and it'd be down to fine little details about whether one method is better than another. Well, actually, it wasn't like that at all, and the average conference that dealt with this was more like this. You had a situation where every different experimental group had different values for these band or sets, as they're called. They even non-overlapping error bars, all right? And everything we're taught about errors as students, and make sure that everything is properly quantified, and so that everyone will agree that you agree within the error bars. Well, there were non-overlapping error bars. It was just absolute bedlam, because the conferences then just became a matter of screaming and shouting in each other and claiming that your method was better than someone else's. And it was just like, wouldn't it be good if we could just put a stop to all this and get the answer? Okay, so that's the sort of thing that in principle we can predict quantum mechanically, except we can't solve the equation. So, okay, that's one example. Another example is another area of science that was developing again in the 1980s. This is just showing my age, of course, which was understanding and being able to look at properties of surfaces in more detail. An interesting thing about this technology is that what enabled studies of surfaces and atoms or molecules at surfaces was actually just being able to create very, very good vacuum conditions so the surface would remain clean. And that was what was developed in the 1980s, which then led to the whole of the area of surface science, okay? But if you go to the very early experiments, on these clean surfaces, all right, you'd have some sort of material. And what you might do in a sort of, molecular beam experiment is you'd have a source of molecules which you'd fire at the surface, and then you'd have a detector that could look at molecules scattered from the surface. And you had, well, firstly, the experiments were slow, and you didn't have many things that you could vary. Even if you could vary more things, because the experiments were slow, you couldn't explore very much. But if this is a molecule interacting with the surface, well, the surface has got tons and tons of atoms in it. The molecule might only have a couple of atoms in it. The detector's just picking up what is scattered from the surface. Your problem is that you have measurement capability in just one or two parameters, but an interaction that is multidimensional, just like a traveling salesman problem. And the result, of course, was the same sort of thing. So people would basically dream up their own prejudices of what happened when the molecule reached the surface, just shown schematically with this sort of contour diagram here. In reality, these potential energy surfaces are massively high dimensional, all right? And people could do whatever they like. And of course, they could play around because you have so many parameters. You could play around with whatever your prejudice is of what was happening in the system and fit experiment. So what were surface physics conferences like, or surface science conferences like at the same time? Exactly the same thing. Bedlam, people arguing about their prejudice of the potential energy surface. No one really getting anywhere, okay? So what put a stop to all of this? Well, we know or knew that quantum mechanics would allow you, without any prejudice, because you had fixed equations, just put in atomic numbers, you didn't put in your idea of what was going on, your view of the science. That, in principle, is enshrined within the quantum mechanics. Paul Dirac says, yes, it's all there, but we can't solve it. To be fair to Paul Dirac, he then subsequently said this following sort of thing after that quote I showed before, is what you really want is approximate methods that get you most of the way to the answer, but are tractable. Okay, and that's actually very good advice to anyone doing research. Yeah, don't make it intractable. The thing was, I mean, he said this in probably about 1930 or so, and it was, well, 50 years before it was shown that you could actually come up with approximate methods that do pretty well. Interestingly, the idea, the methodology that established this is a thing called density functional theory. That's really not important. It's just a name. The theory itself was, proposed in 1964 and then 1965 for the follow-up publication. It took a further 15 years for everything to have come together into a tractable, pragmatic solution. And that's just illustrated in the next slide. With all these things, people can argue about what was the very, very, very first paper that proved everything worked. But this is certainly one of the very earliest. It's showing silicon again. So thanks to Eleanor for showing you silicon. It's a lot simpler than what she showed because it is just the perfect crystal of silicon. Okay. But what these authors showed was that you could take just the atomic number of silicon or its name or its symbol, put that into quantum mechanical equations with density functional theory as a way of making a tractable solution. And whether on the left, this is just looking at different crystal structures, showing that the diamond structure has got the lowest energy. It also is telling us a little bit of what's going to happen if you actually try compressing the silicon. It will actually change to the beta tin structure. That's what that line is in the figure. The other tables just show other properties, all of which were computed from density functional theory with the same input in the same way. And that, of course, is showing one of the great things about doing computational work. You don't need a different piece of experimental apparatus to do each different property. You all just put it into the computer and out pops the answer. So there we are. We have the realization of Dirac's vision of let's have a approximate solution to quantum mechanics that actually tells us useful information. And we're there, which is great. Except there's always a but. That's why there's always research to be done. Turned out that this methodology and the way it was implemented then was great, but it only worked for a few atoms, so silicon, things around it. You couldn't actually, using that approach, make it work for carbon or oxygen or complicated many electron atoms like copper and iron. And so you had, even more annoying. I mean, with quantum mechanics, you have, well, it's kind of an equation and we can't possibly solve it. Then you get to this level of density functional theory and it's, well, we can actually get something useful, but we can't do it for most things that matter. So what happened next? Well, what happened next was, having vowed I was never worked with computers, I was looking for a postdoctoral position. I visited MIT. I met John Johnopoulos, who was working in this field. And, John, well, okay, so let's be honest about it. I didn't get the offer to work at Bell Labs because I wasn't good enough. I did get an offer to go and work somewhere else, and I won't possibly say the name of the university in North America because I just found it was so boring I didn't want to go there. I went to MIT, which didn't have a reputation it has now at that time, and certainly not in this sort of field of work. But John Johnopoulos was just like an inspirational, supportive leader. And I thought, okay, I'll go and work with John. I know he does computation, but it just means pressing a button and getting some calculations done. That's fine. I can live with that. Okay. So I arrived at MIT in early 1985, and I would have just been pressing a button, getting a few simple calculations out with density functional theory, and I'd have been perfectly happy. But this is where the facts or information changed again. These two Italians, Roberto Carr and Michele Paranello, who were working Trieste, found a combination of mathematical methods that allowed you to do density functional theory calculations on somewhat bigger systems. All right, it jumped from 2 to 8. But that was quite a big deal. They also allowed you to start moving the atoms around much more freely and do dynamical simulations, and it was all very, very good. Interestingly, all the things that they put together to make this work were things that people had been trying, but just not put together in the right way, okay? Rebecca Carr consulted IBM. John Giannopoulos met him at IBM, Yorktown Heights. John immediately saw this was a way forward for density functional theory. And so he did what all American professors do, having consulted IBM, got his fee. He came back to Boston. Did he come into MIT? Oh, no. He went up to Corning Glass, got another day's consultancy telling Corning Glass that this was the way of the future, then came back to MIT, called a group meeting, and I was sitting in the back, not really paying very much attention, and he was going on about the methodology, and I sort of vaguely remember him saying, and you're going to set it up. So I was kind of looking around the room to see, which of his brilliant students who actually knew how to code he was pointing at, and discovered he was pointing at me. Anyway, let's fast forward 7 years, okay? And this is where I'm going to have to hand over to the people in charge, because they're going to show a very, very short video clip. Remember, we had the problem of what happens when molecules hit surfaces and everyone argued about it? Well, in this video clip, we simply specified atomic numbers of silicon and a chlorine, and we just let quantum mechanics decide what was going to happen. And if it runs... Okay, so let's point out a number of things. Everything looks very fuzzy because computer graphics wasn't very well advanced in the 1990s. We actually had to use pre-production software to create these animations. The fuzzy bits are where the electrons are. So Eleanor talked about electrons. That's where they are, and they're just density contours. So yellow is high density, blue is lower density. And if we just run it once more, so the thing on the top with the green blobs is, the green blobs are chlorine. So it starts as a chlorine molecule. It approaches the surface. It dissociates. See, the silicon atoms are moving around. That was some people knew about that, but a lot of people thought that surfaces were just like inert and didn't do anything. Actually, far from it, those silicon atoms go chasing after having split apart the chlorine bond, the silicon atoms go chasing after the chlorines because they want to bond to them. They want to form new bonds because that's energetically favorable. We saw all of that in the simulation. Lots of suggestions of things that happened in those potential energy surfaces turned out to be complete and utter nonsense. Okay, that's enough of the little clip, so let's go back to the presentation. So that simulation was 100 atoms. We'd done 400 atom simulations. We were moving things around. We were letting the computer tell us how the real world behaved. We were showing that most of the ideas that people have proposed for why things happened were completely wrong. There's the reference to the paper. I won't dwell on that. In fact, was it a big deal? Yeah, it was a big deal. I mean, the same year, Adrian Sutton, who was at Oxford in the materials department, used a picture from our animations on the front cover of his book. It was a big deal back then. It's now kind of like routine. You'd have liked to have thought the whole community would be behind you. And I can assure you they were. They were behind us and stabbing us in the back. So, about density functional theory. What did every chemist say? It doesn't work. What did they then say? Having said it doesn't work, they'd then say, what is it? So they didn't know what it was, but they knew it didn't work. Okay? What did the physicists say? Why do we need more than 10 atoms? I mean, for goodness sake. And this was a great one. Okay? A UK scientist, this is in the 1990s, for goodness sake. We were told that UK researchers are not meant to be world leading. All right? I mean, for goodness sake, this is ridiculous. Okay? Okay, I have a thing about the chemists. This gives some sort of idea of a meteoric rise of density functional theory. Do you like the units of kilopapers? So this is thousands of papers a year. Some estimates, you can see this runs out 2011. Some estimates are about 30,000 papers a year published with density functional theory. Remember all those flaming chemists saying it doesn't work? Well, in 1998, they gave the Nobel Prize in Chemistry to a physicist, the person who developed density functional theory, Walter Kohn, and rewrote history to pretend that they were always interested in it. All right? It really is sickening. Okay, so I know I've only got a few minutes left, and I meant to give you some lessons. And one of these actually has been touched on sort of already. And they are lessons I've learned from my science that I think tell us an awful lot about where we are and what we're trying to do in science and as humans in our life, okay? So Amdahl's law, for those who go back into the prehistory of computers was basically just a touch base get real about using either faster processing units alongside slower ones, or using many processing units in parallel computers, or perhaps even using quantum computers in the future. And what it says is, it's all very well putting off part of your calculation to a much faster processor, but the problem is that depending on the relative speeds, you're going to be limited by the slowest bit of the computer, okay? So if you talk about multiprocessor computing, right, you may be able to put large amounts of it onto the multiprocessor bit, but there will be a rump that can only run on one processor ever. And depending on what fraction of the calculation it is, that will limit how fast you can actually run the calculation. And any further effort you do speeding up the fast bit is completely unwasted. You've got to do the hard bit, okay? So what does that reflect in terms of, real world? Well, capability is limited by the weakest link. And I suppose if there's one thing I get so annoyed with academics about, well, they've always done this. I mean, the thing about academic research is you can define your own problem, yes? And academics do have a wonderful tendency to essentially solve the trivial part of the problem and then pass on the difficult bit to other people. And I would like, I hope that lots of you in the audience want to do important, useful things, in which case, think about the whole solution. Think about, will the whole thing work together? Don't just focus on one bit that's easy. If you can't make progress on everything, if everything isn't fit for purpose, then you may do something wonderful, but it's not going to get to the real world. And as I said, I kind of lost it with academics because they're really very poor at that. The next, actually, this is a sort of, life dilemma problem. So we already had reference to the traveling salesman problem in one of the lightning talks, the difficulty of working out your perfect route between every single city, minimizing that path, and how quantum can actually help you do that. This was actually a very relevant question in the early days of computers. I mean, we're talking about so far ago where your adder unit was actually several different pieces of silicon, and so you had to connect them with wires, and the same with the multiplier, and the same with the memory. And you were getting to a point where you had computers had so many different things that had to be put together, and you were trying to sort of minimize the amount of wire and the amount of time and all the rest of it. And it was basically equivalent to a traveling salesman problem. And you were reaching a point where you were spending longer working out the solution to that optimum path problem than the lifetime of the computer. Clearly intractable. So actually, it's physicists who solved this problem, and it is that method of simulated annealing. All right, we heard about quantum annealing. So simulated annealing is finding a way of getting to a good solution, but probably not the perfect solution until you get your quantum algorithms working perfectly. But you find a good solution in tractable time. And I'm not sure if you've found this yourselves. I mean, I spend a lot of time sort of advising students on what they should do, where they should go into academia or industry and all the rest of it. And, what I think we're very good at doing as humans is very rapidly getting rid of the choices which are poor. And then, do you find this? You spend hours and hours and days and weeks trying to decide between the last three. And the reason it's difficult is because there is no definitive answer. Actually, it's not like the traveling salesman problem. Go right back to, that slide at the beginning. Your information will change as you learn more about the things. Yes? Let's say you're applying for a number of jobs, all right? You don't know about the organizations till you go in there, okay? And when you go in there, you might suddenly find one place has got brilliant coffee machines and brilliant breakout spaces, and suddenly, your information has changed. And what would be the point of solving that traveling salesman problem? Actually, that you need to make progress, get rid of bad choices, but once you've got down to a bunch of good choices, actually, it really doesn't matter. And you probably won't know the final discriminator until you start progressing down that line. And I'm running out of time. I've only got one slide to show. It's my, series of slides that all linked together. So my advice as, postgraduate students who want to, move on, what you have to do is make sure your work stands out from that other people are doing. Okay? Now, nowadays, everyone says, oh, I'll do that by doing 110% effort and blah, blah, blah. It's not about that. It's about positioning yourself so you're doing something that stands out. Now, if you're better than everybody else, it's straightforward. If you're at the same level as everyone else, how do you make yourself stand out from the crowd? Well, go and do something that other people aren't doing. Okay? Right. You've got to be seen nowadays. All right? So if this isn't happening already, make sure, it's actually one of the jobs of the supervisor. It'd be interesting if this is part of the contract that the National Physics Lab have as part of their postgraduate supervising contract. You've got to be seen. People don't read the literature anymore. So if you want your work to be noted, you have to be presenting it. And if you're presenting it, people understand it's your work, not your supervisor's work. So demand that your supervisor do that. Okay? Right. If you want to continue in academia, all right, I think probably my advice would be don't. But anyway, if you do, reflecting some of my comments earlier on, choose a postdoctoral supervisor who will at least allow you to do some of your own work, independent work, as well as doing the day job that you have to do on the research project. Okay? But ideally, if you're going down the academic route, the way you really show that independence, do things that other people aren't doing, is get yourself a fellowship so that you actually are beginning to do your own independent research. As I say, develop your own research identity. And with that, I probably overrun my total time, but I will stop. Thank you very much indeed.
Great, Mike. Thank you. Thank you very much. I think we've got a couple of minutes. If you could, I've got one question that has come in. If you could answer it in a couple of minutes. So Richard B. has asked, how do you determine objectively the fidelity of the simulation? I used to work in testing and modeling and simulation of aircraft, and it is not yet certain that we can do this.
Oh, okay. So, I mean, what we are doing is we are predicting properties of materials, some of which have not yet been made. So you make the prediction, and then, if it's within range, someone will go off and do the experiment. And if every time they do that, they basically, as I say, we're not doing quantum mechanics exactly. We don't expect perfect fidelity. So, we're talking about typically 2 or 3% accuracy. So if you're within that, then, and you've done that quite a number of times, yes, of course, there may be exceptions. There are certainly cases where density functional theory works really, really badly, which is why we want these quantum computers, so we don't have to use this approximate method. But there have been plenty of cases where people predicted, new materials. You go away, you do the experiment, and sure enough, you find them. Or you find that if you press on a material like that silicon, it changes to a different crystal structure. Endless predictions of that sort of change, which have then been verified experimentally. So it's really a vast body of predictions then verified by experiment. But if I'm honest, the real value of this technique is not to say, oh, we don't need the experiment, because actually complexity will always get you in the end. It's put the two together and an understanding and move your field by the insight that the modeling can put alongside your experiments.
Great, Mike. Thank you very much. Entertaining and enlightening all at the same time. So thank you very much for that. Right, I need to move on to the next bit now because I know our presenters from the lightning talks are sitting there going, "Is it me? Is it me?" So what I'd like to do now is hand over to Carol Fletcher. Carol is the BT's head of the Thomas Flowers Network, as well as academic and research partnerships to lead on the prize-giving piece. So Carol, over to you.
Thank you, Mike. So hi, everyone. So the judges and I have had our huddle, and I'm pleased to say that we have come up with the result. It was absolutely not an easy job to do that. So my thanks to the judges for kind of persevering and making it through. I just wanted to say congratulations to all 6 of our lightning presenters today. Congratulations for making it down to the final 6, and thank you as well for sharing the work that you're doing. I think Hannah mentioned the 4 V's of big data, and I think we had all of those in the presentation. We absolutely had variety. There was clearly a great volume of research going on behind the talks that we saw. Veracity, and thanks to Mike and his timing, then absolutely velocity too. One of the things I've been doing actually while we've been listening is kind of jotting down people here in BT that I think need to know about some of the work that some of our lightning talk presenters talked about, and others on the call and on the conference. I would really encourage you to think about the same thing and making those links, because we know that, you know, successful research is absolutely a team game. It's multidisciplinary in nature, and nobody solves big problems working by themselves in isolation. So I'd really encourage you to do the same thing. Just before we make the announcement, just to keep you hanging on a little bit longer, I'm just going to ask each of the judges to give some reflections and remarks on their thoughts on the lightning talk. So Kishore, can I hand over to you first, please?
Okay, thank you. And let the clock start ticking at this point of time. So I'll start with, I'll go in chronological order. Frank, that was a very, very powerful, motivating statement. I do software myself. It hadn't occurred to me that there is such a big gap between inefficiencies and then code actually matters in that sense. So I learned something else. Kakia, the problem that you have is a very exciting one. And I would imagine that, you know, in sociological research, this sort of an approach would bring great dividends. Lynn, the piece that you had, I think, resonated with me in multiple ways, mostly and most of all because I knew nothing about the topic and I know a little bit more about it. So thank you very much indeed. Daniel, the work that you presented, I think, touched me in at least one way, and I thought that was superbly presented. What I learned is really the bit about the application of approach to discrete optimization, and I do discrete simulations, and this hadn't occurred to me. So thank you very much, Hannah. The challenge that you put out there in terms of infrastructure and how big data can be used to sort of derive patterns and therefore make changes, I think was a very, very I think the second order effect would be behavioral changes. So I think this would be a very, very good research path to take. Eleanor, to be perfectly honest, when you flashed your title, I was wondering what on earth is this? I think I'm left with the notion that not only did I understand what you said, I think the next time I do a presentation to a crowd that doesn't know what I do, I will try to adopt an approach that you had. So more power to you on that. So my feedback, every participant. And I think I've come below 2 minutes. So thank you.
Thanks, Kishore. Very good. I'm going to pass over to Philip now.
Presenters in order. So Frank, I think, you know, what these software developers know about sustainability, that's a great theme. I thought you set up the presentation really, really well. I think maybe you could have done with 30 seconds more at the end just to get that, the big thing, but really interesting presentation. I think Kakia, the political test classification using neural networks, I think it's fascinating research. And a lot of people at the business school are interested in leadership and text-based research for sure. Fascinating study, particularly, you know, the improved accuracy you got on the text. I think Lynn, really enjoyed your presentation. Visually very interesting presentation. You know, the physically plausible spectral reconstruction. I think I learned a lot, particularly about color fidelity and spectral accuracy. That was some great results there, I think. Daniel, quantum annealing, again, echoing Kishore, the discrete optimization and just how to manage that better. Again, hugely important subject, and again, I learned a lot from that. Hannah, the smarter Suffolk, the kind of combination of IoT and big data, particularly for, you know, big social issues in the region. Fascinating combination. Well done. Some really great work with that. And Eleanor, I think on the quantum entanglements, I think very imaginative presentation. Really enjoyed it, along with very, very strong content. And I guess just to summarize overall, I think all the presentations we saw were very compelling. I think they're all on very important themes, all extremely well presented. I can only imagine the amount of rehearsal we did to get them onto, you know, in terms of under 5 minutes. So fantastic job. I was really, I've learned a lot from them. So thanks a million.
Lovely, thanks Philip. And thank you. Pass over to Trevor.
Okay, so first of all, just thank you to all the presenters, and you know, rather than echo the points that Kishore and Philip made,
made, I really just wanted to say, you know, it was wonderful just to see that energy and passion from everyone, you know, and really just met the purpose of the Tommy Flowers, ranging from fundamental physics all the way through to software engineering, and how those topics have such a massive impact, you know, on our lives. And for me, you know, I saw for each and every presentation, I saw the absolute relevance of something that we're doing here at BT Labs in terms of how we actually progress the state of the art of communications and meet our purpose, you know, to use communications and to, you know, to make people's lives, you know, better through that. So thank you for each and every one of you. I think 5 minutes is certainly, you know, it's very tough to get everything across. So what each of you have done is really enticed me to go and read and understand a little bit more about each of those domains. So you've really whet my appetite to learn more about what you were telling us about. So thank you for that. And as I say, just thank you for the wonderful energy you brought to the presentations.
Lovely. Thank you, Trevor. So we won't keep you waiting any longer, and in kind of a time-honoured tradition, we're going to go in reverse order. And I have to say, obviously, if we'd have been having a physical conference, we would have had a nice presentation now. So we do have some prizes, which we will be getting out to those who've won them. So in reverse order, in third place, we have Yi-Tun Lin from the University of East Anglia. In second place, we have Daniel O'Connell from UCL. I feel we should clap, but no one would hear if we all did that. We can. Congratulations, Yi-Tun and Daniel. And finally, our winner today was Eleanor Crane from UCL. So we will be getting these envelopes winging their way towards you. I think we'll have to get in touch to get postal addresses for you all. But congratulations to our winners and to all of our lightning talks. As you know, as we've said already, they've been absolutely fantastic, and it's been a real honour to listen to them. So I think I'm passing over to Fraser now.